All right, the purpose of this video today is going to be to try to be able to solve for AC circuits. This one specifically is going to deal with if I have a resistor and an inductor in series with each other. This is covering lesson 1 of AC theory level 2. So, in one example here, we've got a source voltage of 150 volts, and we have a resistance voltage of 130 volts. So, if you look on your pink sheet, I'm not going to put a pink sheet up on my screen because you guys have one or have been given one already, at least one. So you guys should be able to have yours there. But if you look at the bottom left-hand corner of your pink sheet, you will see 3 triangles. One of them is a power triangle with voltamps, VARs, and watts. One of them is an impedance triangle with resistance, reactance, and impedance. And the third one is the voltage triangle, and that's specifically going to be the one that we're talking about in this question, or this example, is going to be our voltage triangle. And you can see that you have the resistive voltage, you have reactive voltage, and you have, which your reactive voltage obviously is going to be based on your inductor, your inductive reactance or capacitive reactance. And then I'm going to have my total or source voltage, E total, which is going to be my hypotenuse. So we've talked about this in class, and hopefully you guys know and understand and remember this. The resistive values are always going to be found on the horizontal because those are the ones that are in phase. Voltage and current are always in phase on the resistive branch. So it's the one that's out of phase that's going to be the inductive. So, and all of our totals are going to be on our hypotenuse. Like our total opposition to current flow, our impedance, is on the hypotenuse. Our source voltage, E total, is on the hypotenuse. Our total power consumed by the circuit, voltamps, or apparent power. So we're going to do a lot of this, a lot of these calculations are going to be based off of our right triangle when we are doing these calculations. So I have my hypotenuse value, right? I have 150 volts of source voltage, and I have got my resistive voltage, and my resistive voltage in this case is 130 volts. So we know where to put those because, again, this adjacent side is always going to be based on my resistive values, either my ohms of resistance, my resistive volts, or my true power. Power being used for useful work, consumed for useful work. So in this case here, I've got my 130 volts of resistive voltage, and I have a total or source voltage of 150 volts. So this, I mean, I'd like to make it more complicated than it actually is, I guess, but it's Pythagorean theorem, where we know that a squared plus b squared equals c squared. But in this example, we have c, right? We have the hypotenuse. So we're going to have to take, I'm going to punch up my calculator here. Your guys is fancier than my computer calculator, but I'll do the best I can with what I got. So I'm going to take my 150 and square it, and I got to subtract 130 squared because a squared plus b squared equals c squared, which means that a squared equals this c squared minus b squared. So I'll write that down. So if a squared plus b squared equals c squared, but I know c and I know b, let's just say I know b, I will say that a squared equals c squared minus b squared. But I'm not looking for a squared, I'm looking for a, so I got to take the square root of both sides. So that is going to give me that a equals the square root of c squared minus b squared. So when I do my calculation of c squared minus b squared, I get a value of 5,600, but that is what a squared equals, so I need to take the square root of that. So you guys could do a second square root, second answer, or you could have started that already. When you could have hit second square root of 150 squared minus 130 squared. If you don't understand that, then feel free to ask me about it in class or shoot me a text. All right, so that gives me a value of 74.83 volts used by the inductor. or dropped on the inductor. So when you look at this calculation and you say, man, 74.83 and 130, that's not 150. But if you take your now a squared plus b squared equals c squared, and you take your 130 and you square it, let me punch the calculator back up. If I'm just going to take that value and square it, add 130 squared, I just hit my microphone, sorry. Add 130 squared, equal, and I take the square root of that answer, I should get my 150. All right, so we can check that. All right, so now the only other things that I can really kind of solve for, they didn't give me a total current, they really didn't give me any other values. So what I can do now is I can figure out what my power factor and my phase angle is. So my power factor, if you look on your always true in the center column, you will see that power factor equals the cosine of theta, or resistive volts over total volts, or R over Z, no, R over Z, I'm sorry, is the series side. So, but I can always use my my watts and voltamps, but I don't have those. So I'm going to have to go to my left-hand side. It's always the cosine of theta. So in this case, that's what I'm going to use, the cosine of theta, and theta being where it is, cosine is the adjacent over the hypotenuse. So I'm going to take my 130 volts and divide it by 150 volts, and that is going to give me a value of basically 87%. So I have 87% power factor in this circuit, which means that 87% of the work that's being done is useful work, not waste. Okay? So the only other thing that I can figure out from here is what is the phase angle then. So I've already figured out what my power factor is of 87%, 86.67%, how accurate you want to be. Now I have that value of cosine, and hopefully we remember that the way we find our phase angle now is we just do, because we use the cosine function, we're going to now use the inverse of cosine. And when we do the inverse of cosine, we will see that that is about a 30 degree, about 30 degrees out of phase. So because this is an inductive circuit, it's Eli, right? Eli is inductive. So that means that my voltage sine wave will cross 0 30 degrees, approximately 30 degrees, 29.93 degrees sooner than my current sine wave. Okay? So I'm going to stick on with this. We're going to do a whole circuit now. So I'm going to actually try to strategically do that where I could fit them both in the same picture, but it doesn't look like it really worked out for me. I'm pretty freaking close though. All right. Throw that in the trash. Come on, meow. All right. So now we have our circuit. And I went ahead and picked one that's not, super duper challenging, but it's going to take us a couple of steps. So we see that we have a resistor value of 1500 ohms. And that resistor value is going to come down here, 1500 ohms. All right, and I have a source voltage of 120. So what I'm going to do is we're going to figure out everything that we can. We're going to do PEIZ for impedance. We're going to do PEIXL for inductive reactance, and we're going to do PEIR for the resistor, and the resistor value we know is 1500 ohms. And we know that our source voltage is 120 volts. All right, so that's everything. Now, this 10 henries, those are not in ohms. So I have to convert those 10 henries into ohms in order for me to put this into my triangle. How do I do that? Hopefully, fingers crossed, we remember that we have to do XL in the always true column. XL equals 2 pi FL. So I'm going to take the JATC's recommendation of using 3.14 times 2 is 6.28 for pi, or 2 pi, times F, frequency of 60 hertz, times my induction value of 10 henries. And now I have an inductive reactance of 3768 ohms. Is that correct? Yeah, 3768. So now that I have that value, 3768 over here, I can now solve for my impedance, right? I can do a squared plus b squared, and that'll give me my impedance value. So I'm going to take that value that's still in my calculator, squared, plus 1500. And again, you guys can do it a better way than I can because I'm using this calculator here on the computer. All right, so I get that value. That is c squared. So I want to find out what c is. I got to take the square root of that, and I'm going to get an impedance of 4,000. Well, let's just call it 4,056. So we're not dicking around with it. So 4,056 ohms. Actually, no, I'm going to write voltage in a different color. Really? All right, so this is a series circuit, and hopefully we remember that the same thing in series is current. So I'm going to solve for my current value now, and I'm just gonna leave that value. I'll actually change over to 4056. So I'll go with my 120 volts divided by 4056. And that's going to give me a current flow of, it looks like 0.03 amps. Okay, so I will go over here, and this will be 0.03 amps. And again, I'm in a series circuit. That means that it's 0.03 amps all the way across. Everybody with me so far? Cool. All right, so now I'm going to come through and I'm going to solve for my other two voltages because I know my source voltage, and I'm going to go ahead and write that up here too. So this is 120 volts because, again, if you look on your pink sheet on the bottom left-hand corner, series circuit, you can see that, again, voltage is always, or I'm sorry, the resistor, everything that's involved in the resistor is always on the bottom, everything in the totals is on the hypotenuse, and everything has to do with reactance is on the vertical. So this 4056 is because of impedance, and this is XL, and this is R. This one here is E total, or source voltage. So now I'm going to have my resistive voltage here, and this is going to be my reactive voltage I'll have over here. Okay. So let's figure out what my voltage drop is going to be at my, we'll do the resistor. Now we'll do them in order. Let's go ahead and do the inductor. So we'll do our 3768 times 0.03 amps. And that is going to give us a voltage drop on our inductor of 113 volts. And now we will find our voltage drop across our resistor. 1500 times 0.03. And that'll give me 45 volts. So I'm going to go ahead, because I'm a chicken, I'm going to go ahead. I don't know if you guys could see that, man. S&P just went down. All right. So I'm going to go ahead and check that before I make sure I make too big a mistake here. So I'm going to say 113 squared plus 45 squared equals that. And I'm going to take the square root of that, and it's 121.63. So we're close enough. Remember, we rounded that current, and we also rounded the voltage value of our inductor. So that's close enough for government work. All right, so now I know those values. I'm going to go ahead and plug those in over here too. So my voltage at my resistor is 45, and my voltage at my inductor was 113. And we a squared plus b squared both of those, so we know that those are true and correct. All right, so last but not least, we're going to sit here and we're going to figure out what our power consumed is. And our power consumption is going to be the exact same thing. We are going to use our calculator, and we will see that our power, total power, 120 times 0.03, because it's I times E, right, is 3.6 volt amps. Oh, I got fat pen on black. And then I have got 113 times 0.03 for my reactive power, 3.39 VARs. And now I'm going to take my 45 times 0.03, and that's going to give me 1.35 watts. And I'm not going to write those onto my triangles, get a little crowded up. But what we are going to do is we're going to check this too. So I'll take that 1.35 and square it, because that's a squared plus now b squared, 3.39 squared, equal, and I'm going to take the square root of that value, boop, and I get 3.6, this is 3.65, so again, with all the rounding that we did, that's kind of what we ended up with. So now the only other thing that I really need to do and figure out is what is my phase angle and what is my power factor. I'm a firm believer in trying to find the power factor first, because then you can just inverse cosine to get your phase angle. So if we remember from like 24 seconds ago, and we did our other problem, we remember that that is, in fact, I'll move this over. We should remember that that is the cosine value, which is either R over Z in the series circuit side, or resistive voltage over source voltage, which is also in the series side, or we can go to always true and use the power triangle. I can actually use my 1.35 over 3.6. But let's go ahead and we'll take, because this value is given at 1500, so I'm just going to do R over Z. Like I said, I can use any one of the three. I'm just going to use R over Z, especially since R was a given value and there's no rounding at all in R. So I'm going to take that 1500 and divide it by the 4056, and I'm going to see that I only have about a 37% power factor on that, because I just moved the decimal point over 2 places to the right. So that's a 37% power factor. And because we did that, now I'm going to hit second cosine. And that means that, and again, this is an inductive circuit, Eli, so voltage is going to cross, the voltage sine wave is going to be about 68.3 degrees ahead of the current sine wave. Okay. And it means also got a lot of waste because of that power factor. So the only other tricky part of this, of all this stuff, is they can ask you what happens if we increase the frequency. So what I'm going to do is I'm going to erase all this crud, and I'm going to go back to that original triangle. So bear with. I hope I don't erase any part of the triangle yet, but it could happen. We're also going to do this on my next video when I talk about capacitive reactance, so I should just draw another freaking triangle at this point. All right, I'm lagging a little bit here. All right, screw it. All right, so they can say, what if, there it goes, you bastard. All right, so now they can kind of do the whole, well, what if we increased frequency? So let's go, and we're going to move our, we're going to move it down a little bit here. So if the question says, like, what happens if we increase frequency? So if we increase frequency, we know that we have got, all right, now the thing's just acting up. We know that XL equals 2 pi FL, right? And there we go. Sorry, guys, this thing's just going apeshit now. So XL equals 2 pi FL. So with XL equals 2 pi FL, we said when we were talking about inductance that if frequency went up, that XL went up. So if XL goes up, what did that do to my line for impedance? It made my impedance go up also, right? So XL went up, impedance went up, and that means that my current flow, because Z goes up, if my opposition to current flow goes up, we know that our current flow goes down, right? So now what did it do to theta? What did it do to my phase angle? Well, it made my phase angle get larger. If my phase angle gets larger, that means my power factor went down. And we can see that because, remember, this is my foam. This is my foam and this is my beer. So I didn't change any of the yellow. I just put more foam in the glass. So my power factor went down, and I can tell that because my phase angle went up. That is always going to be true. Anytime the phase angle gets greater, the power factor will go down. Anytime the phase angle goes down, the power factor will get greater. Okay? Call me if you got any questions. I hope this video helps you immensely. Toodles.